Cracking a mathematical sequence by brute force is often frustrating. If you only look at the numbers and try to guess how they grow, you are relying on luck rather than logic. Look at this specific pattern: 2, 6, 12, 20, 30. If I asked you to find the 100th number in this sequence, you would likely find that raw intuition quickly reaches its limit. To find that 100th term, we need to stop guessing. We are going to build a rule for Tn, the algebraic formula that describes any term in the sequence. To do this, we use 4 specific moves: list, notice, guess, and check. Grab a pen and paper so you can work through the steps as we go. Solving these sequences requires moving past intuition and using a mathematical framework to find the specific rule governing the numbers. Step 1 is to list. We lock our data into a table to match the position of the number, labeled n, with its actual value, labeled Tn. We place the position numbers 1 through 5 in the top row, and our sequence values, 2 through 30, in the bottom row. Step 2 is to notice. We calculate the differences between the values to see how the pattern is changing. Our first differences are 4, 6, 8, and 10. Because these numbers are not the same, the sequence is not a simple arithmetic pattern. We have to look one layer deeper. We calculate the second differences by finding the change between 4, 6, 8, and 10. Each time, the difference is exactly 2. This result identifies this as a quadratic sequence. A quadratic sequence is any pattern where the second difference is constant. Finding this constant second difference proves the structure of the pattern and tells us exactly which algebraic method we need to use to solve it. Now we move to step 3, guess, or make a conjecture. Since the sequence is quadratic, we use the standard general formula, Tn equals an squared plus bn plus c. In quadratic sequences, the second difference always equals 2a. Since our second difference is 2, we solve the equation 2a equals 2, giving us an a value of 1. To find b and c, we substitute our first known point from the table. When n is 1, Tn is 2. This creates our first equation. 1 plus b plus c equals 2. We do the same with the second point on the table, where n is 2 and Tn is 6. This gives us 4 plus 2b plus c equals 6. We subtract the first equation from the second to eliminate the c variable. This leaves us with 3 plus b equals 4, so b must be 1. Now we plug that b value back into our first equation. 1 plus 1 plus c equals 2, which means our c value is 0. We now have all 3 variables. Our completed rule for the sequence is Tn equals n squared plus n. By translating the table data into variables and isolating them, we have identified the specific rule that generates every number in the sequence. Be careful not to stop here. Many different rules can share the same first 2 terms, so assuming your formula is correct after only testing the start of the pattern is a common mistake. This leads us to step 4, check. We need to test our rule against a value further down the table. Let's look at the 5th position, where n equals 5. We plug 5 into our formula, which gives us 5 squared plus 5. 5 squared is 25, and adding 5 gives us 30. This matches our table value perfectly. Verifying the formula against a known term confirms that the rule is accurate and works for the entire sequence. You have successfully identified the rule for this sequence, Tn equals n squared plus n. You can apply these 4 tools to almost any pattern. List the terms, notice the differences, guess the rule, and check your work. Try this on a new pattern. This row of squares is built from matchsticks, creating a sequence of 4, 7, 10, and 13. Pause the video, apply the 4 steps to this matchstick pattern, and post your final Tn formula in the comments. Using a repeatable framework allows you to find the logic in any numerical sequence you encounter.